Hey guys, welcome back to the next video on the matrix multiplication. I'll try to just make a couple of points here. As we ended the last video, if you remember, we started the very first one with the scalar multiplication, slowly went into what it means to multiply two matrices, and we gave an intuition with the example of a pizza and stuff like that. And what I want to do in this video, this video is more about a couple of observations I want to make on helping you understand, although we knew what are the similarities between multiplying two matrices and multiplying two simple numbers. We took those examples in the previous two videos. I told you, if you remember, that there are also some interesting differences between these two concepts of what happens when we multiply two matrices as opposed to when we multiply two simple numbers. Where do they differ and where do they diverge? And that's very important to build a foundation on how should you see matrices differently than the numbers in certain instances. And this video is all about those instances, and this is what I'm scrolling. That's kind of a quick recap of the last two videos. Okay, so let's talk about today's focus on this session. Is matrix multiplication different than multiplying two numbers? Yes. Okay, so let's focus on that one. Let's continue our example on the pizza itself, and let's see what happens. Okay, let's take the first observation over here. Okay, so what are we trying to say? If we're trying to say that observation that sometimes matrix multiplications are not defined or not possible, right? In terms of the way it's structured. In numbers, except for when you kind of multiply it by 0, it's not defined, right? If you multiply 4 by 0, it's not defined. Otherwise, every multiplication is possible in numbers. It will give you some answers, right? But in matrices, there are certain instances where certain types of multiplication is not possible. Let's focus on a couple of interesting instances, okay? So let's take the first instance where we have three matrices, A, B, and C, the same pizza example. We have the type of the pizza, we have the number of orders in matrix B, and the cost, right? So let's say over here we have all the four numbers, and in the order we are missing one of the orders here, right? Instead of having, for example, over here, if you see, we have both the orders. Instead of this, we are missing this part over here. Then what happens when you try to multiply it, right? For over here, when we do the matrix algebra, we take 75 multiplied by 1, we put it here, and then we say add 150, and then we have a missing number because the number this would have been here, that would have been number we would have plugged in there, but we don't have a number, so we cannot complete the operation. And again over here, the same thing will happen, we will not be able to complete the operation. So what happens in essence, what we're trying to see here is, if the columns on the first matrix, the matrix on the leftmost A, the number of columns, so here the number of columns are 2, right? Column 1 and column 2. If the columns on the matrix A and the rows on the matrix B, on the rightmost matrix, the rows over here, this is row 1 and this is row 2. This is row 1 and this is row 2. If the columns on the leftmost matrix do not match the rows on the rightmost matrix, then the multiplication is not possible, okay? Let me repeat it once again. If the columns on the leftmost matrix, the number of columns, here the number of columns are 2, if it does not match the number of rows in the second matrix, row 1 and row 2 here, then the matrix multiplication is not possible. For example, over here is an instance where it's possible, right? We took the same example in the last two videos, right? For example, we have matrix A, we have matrix B, and we have C. So the number of columns here, these are the columns. This is column 1 and this is column 2, right? This is column 2 and this is column 1. So number of columns on the leftmost matrix is 2, and number of rows, this is row 1 and this is row 2. Both have numbers. There are 2 rows on the rightmost matrix, right? Let me just remove this part here. Okay, all right. So we have got 2 rows here. So these are matching. This 2 is equal to 2, and hence the multiplication is possible, right? There exists an answer for here. So always remember that. So like here I mentioned, A has 2 columns and B has 2 rows, and hence they can be multiplied. Otherwise, it's not defined. That's one example where the matrix multiplication could be different from multiplying two numbers, right? Similarly over here, and the notion, like if you take the pizza example, obviously if you're trying to order a number of pizzas and you say I also want you to deliver some medium pizzas right over here, but if I don't tell how many orders, how is it possible to deliver, right? So if you can take that example, you can understand why it's not possible to multiply the matrices, right? That's how you kind of connect to a real case example. Similarly over here, if you see, I've just slightly tweaked the example. So there is a regular pizza over here, whatever we have here, right? This portion is good enough. And in the number of orders, I have more orders than the number of matching pizzas. So I have the two rows, I have got 3 rows, but I don't know the number of orders. I want 3 of something, 3 orders of some pizza, but what pizza I don't know. So again, there is a missing element here. If you see, when I try to multiply that, there's a missing element here. And again, it's not defined. So what it means is here, what happens is I've got column A, matrix A has got 2 columns, but the B should have 2 rows, but it has got 3 rows. Over here, it had only 1 row. Over here, it has got 1 extra row, and hence it's not defined, right? That's one of the examples that you should know. Normally in the examination, I don't think you'll be tricked to do that, but if something is not adding up, then you can write it, but I don't think such questions will come. But this is the foundation of whether a matrix is defined or not, okay? And in summary over here, there's another way of nicely summarizing it, right? If there are 2 matrices on the right side, if you see, there's matrix U and this is matrix M, let's say, and if you want to multiply those, it's a very simple rule. So first you see what is the number of rows and number of columns on this matrix, and you always write the rows first, followed by the columns as a denomination or as a more of a nomenclature. So over the rows here is 3, and the number of columns is here is 2, and here is the number of rows, and here is the number of columns, right? So what we are doing, this is the leftmost matrix, this is on the left side, and this is on the right side. And what we are saying is the matrix on the left, the number of columns, right, should match the number of rows on the right. So the numbers closer here this way. If you see this way, it's a better way of understanding. This 2 is equal to 2. Then the multiplication is possible. And what will be the net matrix, the final matrix, the answer, how many rows and how many columns it will have, that will be determined by the other 2 numbers. The final matrix will have 3 rows and 3 columns, right? 3 rows like this and 3 columns. So whether the multiplication is possible or not, that will be determined by the inner numbers, which is the column on the leftmost matrix, whether it matches to the number of rows on the rightmost matrix. But if the multiplication is possible, what will be the net answer, the net matrix, how many rows and columns it will have, that itself will be determined by the other 2 numbers, where whatever number is on the left matrix, this is the number of rows and this is the number of columns. That's kind of a cheat sheet here. And same thing in terms of words, it's kind of explaining here, right? Left matrix and right matrix, I told you, right? If I'm saying matrix NB, the A is on the left side and B is on the right side, and that's what they're trying to do. They're trying to see A has got 2 columns and B has got 3 rows. So 2 is not equal to 3, right, over here, and hence you cannot multiply it. That's the same thing. Whatever I explained, in case you want to read it out in terms of words and verbiage, it's given here. Okay, that's one of the examples where the multiplication is different than how you multiply on a, like matrix multiplication is different than on the numbers. Okay, then let's move on to the most interesting example on why matrix multiplication or when matrix multiplication will not be same as the numbers. This is the beautiful example, right? So always save the best for the last. Okay, so let's get here. So normally if you see here, these are 2 matrices, right, A and B. So the question is, the observation we are trying to make is multiplying A into B same as B into A, right, or B into A. In terms of numbers, if you see 3 into 4 is equal to 4 into 3 is equal to 12. In this case, if the numbers are the smaller case A and AB, so in multiplication, the order of the numbers do not matter, right? Whether you multiply make it 3 into 4 or you make 4 into 3, the answer is going to be the same, right? It does not matter. But let's see what happens when we multiply 2 matrices and see whether the order, whether A into B is it same as B into A. Okay, let's check that out. That's the interesting part here. And again, let's take the pizza example because it helps you clear your head intuitively what we're talking about. Okay, so let's take the first example, AB, right? This is the A matrix, this is a B matrix. A is on the left and B is on the right. Okay, and A is the type of the pizza. So let's say we're going to make a computer program, and we're going to just tell, hey, I'm just going to give you the numbers, you just multiply, and the number I'm going to give you on the left or in the first data entry is the type of pizza, whether regular or medium or simply veg and non-veg. That's what it is, right? On this one. And then in the next matrix, I'm going to give you the number of orders. The first column here is the number of orders for my family, and the second column over here is the orders for my friends. Now you calculate and how you want to do. So what the computer will do, or how you will do it, you will just apply the same algebra that we discussed. You will take this row and you will take this column first and do the multiplication and the addition, like here 75 into 1, and then you will say plus 150 into 2. That will be the first entry, and the next entry will be, you will take the same row and the same column and apply it on the second entry over here, and then you will take the next row and take the first column and do it here, and the same row and the next column here, and you will do it here. So you will get 4 entries, right, over here, right? And the net result is 375, 825, 535, 1175. This is like the total cost of the veg, and this is the total cost of the non-veg, and this is the regular, and this is the medium size of pizza. That's how you get it, right? And the way, if you see it, this matrix A is a 2 by 2 matrix. Matrix B also has got 2 rows and 2 columns, 2 by 2. And is a multiplication possible? Obviously yes, because we did it. But how do you do that? You take the number of columns on this, take the number of rows on this matches to this. Yes, multiplication is possible. That's a good news. And whatever is the final matrix, how many rows and numbers we will have for that will be determined by the leftover numbers. Over here, this is the first one is the row. The final matrix will have a 2 row, and it will be having a 2 columns, so 2 by 2, total 4 elements, right? And that's how there are 4 elements here, which is just a validation of what we discussed just now over here, right? Over here, this one. Okay, now we have computed AB. Now let's say we are going to compute BA. The first, now the left and right matrices are switched. Now B is on the left side and A is on the right side, okay? But from an intuition standpoint, let's say you're doing the same computer programming, the computer is always going to treat the first type of the pizza, the first entry that you make, as pizza type. The computer does not know that you mentally switched the orders. It will take, okay, whatever you're going to feed me first, I will assume that that's the type of the pizza and the size of the pizza, veg and medium, veg, regular, stuff like that, right? Like how you've done that. But basically, you know that what you're feeding first, factually, it's the number of orders on the pizza, right? And then you're switching it, right, on the left and right. So what happens when you do the multiplication in this case, when you apply the same algebra of taking the left row on the left and column on the right for multiplication, that's how you multiply the matrix algebra, and you finally calculate the result. You see this result and this result are not matching, right? Which proves that in matrix, the order is very important. AB is not equal to BA in matrices, or when you multiply 2 matrix or matrices, unlike when you multiply 2 numbers. That's what this proves, right? So that's one of the most important thing when you do it. So whenever you get examples, there will be a lot of examples which will ask you to do this kind of in some or the other way. So don't get tricked there when you change the order. So whatever is on the left and whatever is on the right matters in matrix, and that's how we'll conclude this session over here, right? So what are we trying to conclude here? B multiplied by A is not same as A multiplied by B, right? It's not same. It will give you different answers by the rules of matrix algebra, which we discussed. And just to clear your head, like I give you, like if you're going to program it with the computer, it changes the whole context, right? In the first example, the computer will treat the first set of numbers as a pizza type and size, and in the second example, the computer will treat the first set of numbers as it will still treat as pizza type and size, but in fact you're entering the order. So the computer does not differentiate. So that means obviously the numbers are not going to match. So you can think about that way, right? And that's a point. And just to give a simple analogy, if you take a date format, how the Indians and the British put the dates versus the Western American countries. They always switch the dates and the months, right? So if you see, this one is like 3rd October, right, in the Indian standard, and if this is like the American standard, what it means is 10th March. Okay, so if you are feeding this to two different computer systems, one on the India side and one on the US side, the computer is going to treat them completely different. Otherwise, it's not going to understand, right? It's kind of the same, this thing where the notations kind of mean a lot. So what does it mean in summary, right? The last 2 points which I've underlined, right? What does it mean in summary? Matrix notation is positional, right? Basically where you put, where is the sequence, where does it lie, whether it's on the left or right, it's very important. And it's important not only inside the matrix, that means if you draw this matrix right here or two matrices over here, the position of the elements within the matrix, whether it's a row or column, inside is important, as well as outside, because if this is A and this is B, and when you switch the matrix and you make it B and A, you're changing the matrices. You're not changing anything on the inside, but you're changing the whole sequence. That's also matters. So when you change it outside, also it matters. So matrix notation is very positional within the matrix, the relative positioning of the data elements, and also among the matrices, which comes first, right? Because like we spoke about the transformation, the matrix on the left has a transformational effect on the right. There is some way, which we'll talk about in the next video, where the matrix on the left kind of transforms the matrix on the right. So when you switch the order here like this, the transformation also changes, right? That's the big difference here. And that's what we're trying to say. AB is not equal to BA in terms of matrices, and the only exception obviously is if the matrix itself has only one element, right? It does not have more than one element, where it basically becomes a number system, let's say 4 into 3. Although these are matrices, it just has one number, a 1 by 1 matrix. There's one row and one column, one row and one column, one row and one column. In this case, whether you write this way or this way, it will be just treated as numbers, how the numbers kind of compute, and the order of the numbers do not really matter. Except for that situation, for the rest of this thing, the takeaways, matrix multiplication, the order of the matrices kind of matter. And whether the matrix multiplication exists or not, that depends upon the number of columns on the leftmost matrix, whether it's same as the number of rows on the second matrix. That will tell us whether multiplication is possible or not. So those are the two important observations that I wanted to just leave it on this video. And the next video is all about transformation, and that's where all the magic happens, which will tie back to the movie Matrix. How do they kind of really code the graphics and the action sequences where Keanu Reeves is flipping and doing a rotation and jumping back and forth and all those things. What exactly they do, how does the computer graphics treat those things? We'll talk about more in those kind of situations. So more coming up, stay tuned. Hopefully you kind of enjoyed the video. Thank you guys.